All right, we have 6.6 today, coordinate geometry of quadrilaterals, and this is our last section before we'll take our test and things. So next week we'll have a test. All right, so first up, our objectives are to determine the vertices of specific quadrilaterals using known properties, and to classify quadrilaterals using coordinate geometry. This coordinate geometry just means they're going to be on the coordinate grid, okay, the Cartesian plane, whatever you want to call that, is where they're going to be. Okay, so let's get started with example 1. Move this down because example 1 takes up a lot of the page. All right, so it says classify quadrilateral ABCD as specifically as possible given its coordinates. So we have A is -1, 3. So I went ahead and I kind of sketched it because we've got some tips here to help us. So the first thing is to sketch it. So we've got A is -1, 3, B is 3, 2, C is 4, -2, and D is 0, -1. Sketched it out there. But again, it's a sketch, so don't use the pictures to help you out. But in order to solve this, it helps to sketch the graph, and then some things we can consider finding are the midpoints of the diagonals, the slopes of the diagonals, the lengths of the diagonals, the lengths of the sides, and the slopes of the sides. So what are those formulas for some of those things? Do you remember? Do you know where to find the formulas? There we go. Yeah. Get out that quick reference sheet. So maybe I'll erase this line here so we can put some of those in there. So if you look at that, if you get out your quick reference sheet, I'm going to pull it up here for a second, and we've got midpoint, distance, slope, and notice it says in the coordinate plane. It's all these things here that we're going to be using today in your quick reference guide. Okay, so I was going to write them up there, but I showed them to you instead, so we can do that. So I started us off, okay, to do that. So the capital M stands for the midpoint of AC. All right, so let's look at that formula. Okay, so if we want to find the midpoint, it is the midpoint equals the sum of your x's divided by 2 is going to be your new x value, and then the sum of your y's divided by 2 is the new y value. Does that make sense? Okay, so for AC, I just took those values, so -1 and 4, and then the y values are 3 and -2. Plugged them into the formula, and we got the midpoint of 3/2 is our x, and 1/2 is our y value. So we need to find the midpoint of BD. Okay, so what are my coordinates if we're using B and D? So my x, okay, yep, we got 0 plus 3 divided by 2. And for my y, -1 plus 2. Perfect. Divided by 2. So 0 plus 3 over 2 is 3/2. Let me put my parentheses back. And -1 plus 2, okay, is 1/2. Well, wait a minute. What do you notice about these two, about the midpoint, the point of the midpoint here, and the midpoint of BD? They're the same. Okay, so they have the same midpoint. What does that tell us about ABCD? Because we have all these theorems and things that we've talked about where they're midpoints. What shape has a midpoint that bisects the midpoints, or the diagonals bisect each other? A rhombus does, but we don't know if it's a rhombus yet because we have other rules. If we, like I'm thinking of the notes that we took that day, or that the notes that we've taken at the diagram, but that may not be the best. So what's the The earliest we know that I just started the answer. The earliest that you know the midpoint or the diagonals bisect each other. A parallelogram, okay? Yeah, so we know ABCD is a parallelogram. And I'm going to draw an arrow. Because they have the same midpoint, we know that it is one of the types of parallelogram. Okay, so then we're going to go a little further, dig deeper. So what's the little m stand for? Nope, the capital M is midpoint, right? So that's the capital M. The little m stands for slope, like y equals mx plus b. Okay, so to find the slope, again, if we go back, we're gonna, and we look at our formula for that, the slope is our y values subtracted and divided by the difference of our x values. So if we subtract them. So I did the slope of AC, that diagonal again, right? It's not in there. We could draw it in our diagonals. Okay, so I found the slope of AC, which is -1. So now we need to find the slope of BD. Good, -1 minus 2. 0 minus 3. So -1 minus 2 is? -3. And 0 minus 3? -3. Okay, so what's -3 over -3 equal? 1, a positive 1. Okay, so what do we know about these? We have a slope of -1 and a slope of 1. What does that tell us? They're opposites. Okay, so they're reciprocals. Well, so here's the thing. They're opposites, so they're what? What does it tell us about these diagonals? Not congruent. They're actually opposite reciprocals. That's a little hard to see because this would be -1 over 1, and this is a positive 1 over 1. So they're the negative reciprocals of each other, which means what? The lines are parallel, perpendicular, or nothing special? Perpendicular, yeah. When we have those slopes that are negative reciprocals, it means they're perpendicular. It's not going to be on the screen there, so it's perpendicular. I'll draw that symbol. So now what do we know? We know ABCD is a parallelogram. We know the diagonals are perpendicular, so what shape can we say that it is now? Okay, so if we go back and look at our theorems, what shape does it get to? Like theorem 6.2.5 is the one that said diagonals of a parallelogram bisect each other. So where can we get when we have the diagonals are perpendicular? Nope, so quadrilateral is above, right? Because like if we were looking at so we have a quadrilateral that's broken into 3 parts. That's where we had the trapezoid, the parallelogram, and the kite. So we're already at the parallelogram. So from the parallelogram, we can have a rectangle, a rhombus, and then from those two, we have the square. So in this logic, we're already at the parallelogram level. Now we know one more piece of information. We know that their slopes are negative reciprocals, or that their lines are perpendicular. So if they have perpendicular diagonals, does that make them a rectangle or a rhombus? A rhombus. Perfect. So yes, ABCD is a rhombus. Awesome. Okay. So the next step on the list is like the length of our diagonals. How long are they? So that's what the next one is, finding the length of our diagonals. So again, on our quick reference sheet, that is there under the distance. So I solve for the distance of AC, but this is the distance equals, when we look at that formula, it's the difference of our x values squared, whoops, plus the difference of our y values squared. Okay, is where that information comes from. So let's do BD together, because I already did AC. So the distance of BD is going to be the square root of 0 minus 3 squared plus, you got it, negative 1 minus 2 squared, which you already did all the math on that, right? We did that math up here. 0 minus 3 was negative 3, so this is negative 3 squared plus, nope, negative 1 minus 2, or you could do it here, is negative 3 again. Oh, that was my plus sign I wrote over. Negative 3 squared. So what's negative 3 squared?
No, 9 squared.
So it would be, okay, well, negative 3 squared is 9. Okay, so this is going to be equals the square root of 9 plus 9, which is the square root of 18. Okay, then we need to practice some simplifying of that. Do you remember how to do that? Simplify the radical? Okay, so what is the square root of 18 simplified?
Would it be 9 square root of 2?
Close. It would be 3, because the 9 is a perfect square, so the square root of 9 is 3. Does that make sense? Okay, because yeah, like if we broke this into 9 times 2, or, well, that's the same thing as the square root of 9 times the square root of 2. The square root of 9 we know is 3. So following that logic. So very nice. Okay, so now we have the length of AC is 5 times the square root of 2, and the length of BD is 3 times the square root of 2. Well, they're not congruent. So from rhombus, now we're at this level, right? We know it's a rhombus. The only other option is to say that it's a square. But in order to be a square, we know that the diagonals of a square are equal. They're congruent. So these aren't equal. So what do we know about ABCD?
It's not a square.
It's not a square. Yeah, we know it's not a square. Exactly. So we did a lot of work. So all we can say is it is a rhombus. We've taken it down as far as a rhombus, but it is not a square. Okay, what do you think about all that? See, this is the part, it's like, okay, I can do all the math with the geometry part. It's like, woohoo, back to some more math instead of the logic part of geometry. Okay, excellent. Then this last little note says properties of quadrilaterals can be used to locate the vertices of quadrilaterals or the intersection of diagonals. So in this case, we can kind of use them backwards. We can use what we know. So example 2 says find the coordinates of F and G if the diagonals of EFGH intersect at T 3, 2. All right, so I gave us a hint there. Okay, because we want to find the coordinates of F and G. So let me go ahead and mark those. So we want to know where is F and where is G. If the diagonals intersect at this T, point T, 3, 2. Okay, so the hint was that T equals the midpoint of FH, right? So if we have diagonals across here, I'm gonna draw my diagonals in green. My midpoint has, or at this point of intersection, has to be the midpoint between F and H. Okay, which may not seem very helpful at this point, except that we do know H. We have a set of the pairs, of the ordered pairs. So we can set this up. Our midpoint is 3, 2, and so we know the formula. It's our x's, we add our x's and we divide by 2. Well, in this case, we don't know the x value for F, so that's why we put an x. But we know the x value for H is 4. And so we're going to have x plus 4 divided by 2. And the same thing for the H, for the next one, sorry, for the y value. We don't know the y value of F, but we know for H, it's 1. Are we good so far? Awesome. Okay, now the cool part about this is that this applies to our x value. So we can actually, so this is therefore, if you remember back from like chapter 2, 3 is equivalent to x plus 4 divided by 2. It's like the corresponding parts, or we're setting equal. And then our y value has to be equal to the 2, like our y expression there. So it's like setting the corresponding parts equal to each other, setting them congruent. So then we can solve. Okay, so in this first one, if I back up a little bit from my drawing here. Okay, so for this first one, we multiplied everything by 2. So we got 6 equals x plus 4. Subtract 4, and we got 2 equals x. We solve this one over here for our y value. We get y equals 3. So F, this is the thing. From this, we found our location at F. It's located at 2, 3. So 2, 3, that looks about right. But we now know where F is located. So we can do the same thing. We're going to use T because this midpoint also has to be the midpoint of this line here of G to E. So we're going to do the same setup. Okay. All right, so walk me through that one. So T is 3, 2, and that's going to equal what?
X
Mm-hmm.
plus 10.
10. We want
0.
0. There you go. Good. Divided by 2.
Then y plus 0.
Good. Divided by 2. All right, so what's the next step? That's kind of where it gets a little tricky for people. Remember corresponding parts.
So would the 3 go to the x and 2 to the y?
Yep, you got it. 3 goes because this is the x and this is the y. Awesome. So we're going to have 3 equals
X plus 0 divided by 2.
You got it. And what's the other one then?
2 equals y plus 0 divided by 2.
Perfect. All right, so to solve it, what are we going to do? Multiply by 2? Okay. Sorry, that's how I wrote that. So these would cancel. 3 times 2 is 6 equals x plus 0, or just 6 equals x. We don't even have to have the 0. Okay, how about the other one?
You do the same, you multiply the 2.
Multiply by 2, okay.
Which would be 4 equals y.
4 equals y. So now we know G, because these are the coordinates for G. G is
6, 4.
You got it. Which again, if we look, okay, if we come over here, we're going past H, so past 4 to 6, and then we're going up to 4. So that looks about right on our sketch. Not perfect, but it's a sketch. It's not supposed to be. All right. Pretty cool, right? Any questions? Okay. You're flying high in class today, man. Okay. And example 3 here. Went off the page a little bit. That's problematic. I try to prevent that from happening, but sometimes it does. Okay, example 3. State the missing coordinates for each figure. So down here on this one over here, this is R, let me make it black, comma 0. So R, comma 0. You will have to have that. All right, so we're stating the missing coordinates for each figure. The first one is a rhombus, JKLM, with diagonals of lengths 2W and 2T. Okay, and the only thing we know, like if we look at this, we've got L over here is W0. Okay, so our X value, we came over W. Well, wait a minute. Our length here is 2W. So wouldn't this distance also be W? Okay, so what's its, we can write its W0. Where did I go from the origin? I went left. Are these positive W's?
Negative W.
Okay, so it should be negative W and 0. Good.
Then would that mean the K's are T's?
The K's are T's. Yeah, if we look at it that way, right, then like from here, since it's a rhombus, right, and all the sides are equal, so that this is T distance and this is T distance. Yeah, so this would be what?
T.
Because my first number is always how? 0, T,
0, negative T.
0, negative T. Perfect. Yeah, that's exactly what that means. Awesome. Okay, how about try B? Isosceles trapezoid OPQR. That's all we got, is it's an isosceles trapezoid. But we have lots of information about this trapezoid. Because where is O?
In the bottom.
Right, it's in the bottom. So what are the coordinates of O?
0.
Yeah, right, this is 0, 0. So then how are we going to describe Q? We really only have to find Q. Because we know P is PH. So what's the P tell us? Left and right or up and down?
Up and down.
The first.
That tells us something.
That tells us the sideways. Okay, so what this is saying is we're coming over, let's see, if I like made this here, right? This distance is P. So what's this? H, that's the height, that's the Y value of how much we went up. Okay, so how's that going to help us with Q? So if we did the same thing and we drew a line down here, okay, so I don't know that that helps us. I might take that line off. Okay, what do we know there? They have the same height. So our Y value is still going to be H. You got it, because they have the same height because it is isosceles. So how are we going to know our X value? So it's saying this point here is that RO.
Would we do B minus R?
Okay, if you did P, think about this. P is a smaller one. Can you take the small one and subtract the big one? R minus P. Yes, we would. This would be R minus P. Okay, because that's that same distance right here to here, because it's isosceles. It doesn't look it, but it is. That is that same distance. So R minus P. Awesome job. That was way good. So R minus P is your X value. H is your Y value. Okay. And then I'm going to put up here, it says example 4, see page 289. I wanted to talk about this proof, but it was a lot of work to include in your notes. So, and it's not really a proof, I guess. But so this one says use coordinate geometry to prove that the bimedians. So this is a term of a convex quadrilateral that we haven't really seen yet. And that says it's the segments connecting the midpoints of the opposite sides. So the bimedians, we've talked about median, but when we say bi, we're talking about both of them. So it's just like if this is the middle, then the connection And this is the middle of this line, the middle of this line, and we connect those. It's that bimedian. Like when we did convex, not convex, the three types of centers to a triangle, we kind of talked about all the different ways to make those. That's where that term kind of like we used the median, and we connected medians to get those orthocenter and incenter, if you remember those, in the circumcenter. Okay, we kind of use that same idea. So that's what they're doing here. Okay, they're proving that the bimedians bisect each other. So what are they finding here with the capital M?
Midpoint.
The midpoint, okay? So they found the midpoint of, and this one was a ton of work. I can't hardly read it. It's not very clear up here. Let me see if I don't want to zoom in necessarily. Okay, so AD and CB, it's much clearer here than on the board. Okay, and the midpoint of DC. So they found all four of those midpoints in there. So this is the work for that. And then they found, so like all of these are midpoints, right? And even the next one, which is kind of hard to see, it says the midpoint of AD minus CB. Well, if I do AD minus CB, what am I going to get there for? What's that going to give me? If we look here, they've started finding the midpoint of each bimedian.
It's going to give you the length of the sides.
Well, this is the midpoint. So if we subtract, if we take this midpoint and this midpoint, and we want to find the midpoint of the difference of those, we're finding the midpoint here of those two. Does that make sense, kind of? So yeah, so this one has a ton of work to it, but also notice that all these, like the work is just letters. It's P and M and Q and B and whatever, and so it looks really kind of messy at the end. So that was one other reason we weren't going to work through it, but I want you to see it and be like, oh, okay, we can do this. So if you're asked to find the bimedians, you'll know what that is in your homework. But you don't have anything this elaborate in your homework to do. So, all right, well, that's it for today then. So you can get started on your homework.